What were the first signs that something unseen was influencing the motion of galaxies? Long before dark matter had a name, astronomers were already encountering a quiet unease in their measurements. When they observed individual stars moving within galaxies, especially spiral galaxies, those stars traced smooth, predictable paths across the sky. Their motion could be measured through subtle shifts in starlight, tiny changes in color that revealed speed. These measurements were not abstract. They were grounded in careful observation, night after night, telescope after telescope. And from those observations, gravity made a clear demand. The mass we could see should determine how fast those stars move. Yet even in the earliest data, something felt slightly off. Not dramatic, not alarming, just persistent enough to resist being ignored. The unease deepened as astronomers began measuring entire galaxies rather than individual stars. By the early 20th century, it was possible to estimate how much mass a galaxy contained by adding up the light from its stars and gas. Light became a proxy for matter. More light meant more mass, and more mass meant stronger gravity. When astronomers compared these mass estimates to the motions they observed, they expected agreement. Instead, they found motion that seemed too energetic, as though galaxies were heavier than their light suggested. At first, this mismatch was easy to dismiss. Measurements were difficult, distances uncertain, instruments imperfect. But the discrepancy did not fade as techniques improved. It sharpened. Before going any further, let me gently say that if this kind of slow, careful curiosity feels like something you enjoy spending time with, a quiet like or a soft tap on subscribe helps keep this channel exploring these questions. And if you feel like sharing, I would love to know where you are listening from right now, wherever in the world you happen to be. One of the earliest and most striking moments came in the 1930s, when Swiss astronomer Fritz Zwicky studied the Coma Cluster, a massive collection of galaxies bound together by gravity. Zwicky measured how fast the galaxies within the cluster were moving relative to one another. Using the same gravitational reasoning that explains how stars orbit within galaxies, he calculated how much mass the cluster would need to keep itself from flying apart. The result was startling. The visible galaxies accounted for only a small fraction of the required mass. The cluster should have dispersed long ago. Yet there it was, stable and intact. Zwicky concluded that some form of unseen matter must be present, adding gravitational weight without adding light. At the time, Zwicky's claim did not reshape astronomy overnight. His idea was bold, but the data were limited, and the concept of large amounts of invisible matter felt premature. Still, the observation lingered. It planted a seed. The universe, it seemed, might be heavier than it looked. As decades passed, other astronomers began to notice similar patterns in different contexts. What had once seemed like an oddity slowly began to resemble a theme. The next major step did not come from clusters, but from individual galaxies studied in greater detail. As radio astronomy matured, astronomers gained a new way to observe matter that does not shine brightly. Neutral hydrogen gas, abundant in galaxies, emits radio waves at a very specific frequency. By tracking this emission, scientists could measure how gas moves far beyond the bright, visible regions of galaxies. These measurements extended rotation curves outward, revealing how orbital speed changes with distance from the galactic center. What they found was deeply counterintuitive. Instead of slowing down, stars and gas far from the center of a galaxy continued to orbit at nearly constant speed. According to classical gravity, this should not happen unless additional mass was present. The outer regions of galaxies behaved as if they were embedded in enormous, invisible halos of matter, far larger than the regions filled with stars. This was not a subtle effect. The difference was large, systematic, and repeatable. It appeared in galaxy after galaxy, regardless of size or environment. At this point, the problem could no longer be treated as a local mistake or a single anomaly. The motions were too regular, too consistent. Something unseen was exerting gravitational influence across vast distances. Importantly, this conclusion did not depend on one particular method or one group of astronomers. Different instruments, different wavelengths, different teams all converged on the same result. When independent approaches agree, physics pays attention. To grasp why this was so compelling, imagine trying to understand a city by watching traffic from above at night. You see headlights moving along roads, slowing at intersections, speeding up on highways. From motion alone, you can infer the layout of streets, even if the asphalt itself is invisible. If cars begin curving where no road should exist, you would suspect a hidden structure guiding them. In the same way, stars were moving as though guided by mass that could not be seen. The analogy ends there, but the intuition holds. Motion reveals structure. As evidence accumulated, astronomers faced a choice. Either vast amounts of matter were present but invisible, or gravity itself behaved differently on galactic scales. Both possibilities were explored seriously. Some researchers proposed modifications to Newtonian gravity, adjusting how force behaves at very low accelerations. These ideas were mathematically elegant and could explain certain galactic motions. However, they struggled to account for all observations simultaneously, especially those involving clusters of galaxies, and later, the bending of light. The invisible matter hypothesis, while initially unsettling, had one powerful advantage. It unified many separate observations under a single assumption. Galaxies rotated too quickly because they were heavier than they appeared. Clusters remained bound because unseen mass added gravitational glue. Structure in the universe formed the way it did because this additional matter influenced how everything else moved. The idea did not solve every problem, but it connected many pieces with surprising economy. Crucially, the early signs of dark matter were not born from speculation, but from restraint. Astronomers did not set out to invent new substances. They followed the data. They trusted gravity, one of the most thoroughly tested forces in physics. When gravity demanded more mass than light could provide, they listened. Dark matter entered the story not as an exotic invention, but as a placeholder for something real, something measurable through its effects. As instruments improved further, the picture grew sharper. Surveys revealed that galaxies are not isolated islands, but part of a vast cosmic web. Their motions within this web, their clustering patterns, and their large-scale distribution all pointed toward the same conclusion. Whatever this unseen matter was, it dominated the mass budget of the universe. Ordinary matter, everything familiar, turned out to be the minority component. What is striking, looking back, is how gently this realization unfolded. There was no single experiment that forced immediate acceptance. Instead, there was a gradual tightening of evidence. Each new observation did not shout, but quietly agreed with the others. The universe was consistent in its message. something unseen was shaping motion on every scale larger than individual stars. This early period of discovery set the tone for everything that followed. Dark matter was not a mystery introduced for dramatic effect. It was a response to precise, careful measurements that refused to align with expectations. The question was never whether astronomers wanted unseen matter to exist. The question was whether the universe required it. Again and again, the answer seemed to be yes. And yet, at this stage, dark matter remained defined entirely by absence. It was whatever caused galaxies to rotate the way they did. It was whatever kept clusters bound. It had no known composition, no detected interactions beyond gravity. This lack of detail was not a weakness, but a sign of honesty. Physics was admitting what it did not yet know, while clearly stating what the universe was doing. As the first signs of unseen influence became undeniable, attention naturally shifted toward understanding how widespread this influence was, and whether it appeared only in certain systems or everywhere gravity operated on large scales. The next step was not to name the unseen, but to map it, to measure it more precisely, and to test whether its effects followed the same patterns in every galaxy we could observe. Because if something unseen truly filled the universe, it would reveal itself not through drama, but through consistency, through motion that remained steady even as our expectations continued to change. The next step was not to look farther outward, but to look more carefully at what was already visible, to measure motion not just as a general impression, but as a precise function of distance. This is where galaxy rotation curves became central, because they transformed a vague imbalance into a sharply defined pattern. A rotation curve is simply a record of how fast material inside a galaxy moves as a function of how far it is from the center. It sounds technical, but its meaning is intuitive. If gravity weakens with distance, motion should slow. If mass thins out, speed should fall away. Astronomers expected rotation curves to rise near the center of a galaxy, where stars are densely packed, and then decline farther out, where there is less visible matter to provide gravitational pull. This expectation was not speculative. It followed directly from Newtonian gravity, which had already explained the motion of planets, moons, and stars with extraordinary accuracy. There was no reason to suspect it would suddenly fail on galactic scales. So, when astronomers plotted these curves carefully, star by star and gas cloud by gas cloud, the result was quietly shocking. Instead of falling, the curves flattened. Beyond a certain distance from the galactic center, orbital speeds stopped decreasing and settled into a steady plateau. Stars tens of thousands of light years from the core were moving just as fast as those much closer in. The effect was not subtle, and it was not confined to one galaxy. It appeared again and again wherever measurements were precise enough to reach the outer regions. The farther astronomers looked, the more mass seemed to be required, yet no additional light appeared to account for it. This flattening carried deep implications. A flat rotation curve means that mass continues to increase with radius, even where visible matter has thinned dramatically. The galaxy behaved as though it were embedded in an extended halo of matter, far larger than the luminous disk. This halo did not glow. It did not form stars. It did not announce itself in any electromagnetic way. Yet its gravitational presence was unmistakable. Motion demanded it. What made this discovery especially powerful was its internal consistency. If the discrepancy had varied wildly from galaxy to galaxy, it could have been dismissed as a peculiarity of formation or measurement. Instead, the same pattern appeared across different morphologies, environments, and scales. Spiral galaxies, large and small, shared similar rotation curves once distance was accounted for. The universe was not improvising. It was following a rule we had not yet named. Radio observations played a crucial role here. Optical telescopes are limited to the bright inner regions of galaxies, where stars dominate. Radio telescopes, by contrast, can detect neutral hydrogen gas far beyond the visible edge. This gas acts as a tracer of gravitational influence in regions otherwise dark. When astronomers extended rotation curves using hydrogen emission, the flatness persisted. The invisible halo did not end where starlight faded. It stretched much farther, enveloping the galaxy in a vast gravitational envelope. At this stage, the idea of dark matter gained clarity. It was no longer a loose suggestion of missing mass. It became a specific requirement with a specific distribution. Dark matter had to surround galaxies in roughly spherical halos. It had to outweigh ordinary matter by several times, and it had to interact gravitationally while remaining electromagnetically silent. These were not assumptions layered on top of the idea. They were consequences forced by observation. The analogy of a spinning carousel helps briefly here. Imagine standing near the center of a carousel at night, watching lights move around you. Close lights move quickly. Far lights more, slowly, because the structure holding them imposes constraints. If suddenly distant lights began moving just as fast as nearby ones, you would infer an unseen structure extending outward, maintaining their motion. You would not conclude that motion itself had changed arbitrarily. You would look for what was holding everything together. Once that intuition is clear, the analogy can be set aside. Importantly, this was not a failure of gravity in the sense of it behaving unpredictably. Gravity was doing exactly what it always does. The failure was in our inventory. We were missing mass. The rotation curves were gravity's way of pointing that out. Every flat curve was a quiet insistence that something real was being left out of the picture. Attempts were made to rescue the situation without invoking unseen matter. Some researchers proposed that the relationship between gravity and acceleration changes at very low values, precisely those encountered in the outer regions of galaxies. These ideas could reproduce flat rotation curves with remarkable precision. They offered an elegant mathematical alternative. But elegance alone was not enough. The same modification had to work everywhere gravity operated, not just in isolated galaxies. As more data accumulated, cracks appeared in this approach. Modified gravity models struggled to explain galaxy clusters, gravitational lensing patterns, and the large-scale structure of the universe simultaneously. Each success came at the cost of another mismatch. Dark matter, by contrast, handled all these domains with a single assumption. Invisible mass existed, distributed in a particular way, influencing motion everywhere. The simplicity was not aesthetic, it was structural. What rotation curves truly accomplished was to remove ambiguity. Before them, unseen mass could be dismissed as measurement error or peculiar circumstance. After them, the effect was geometric, repeatable, and quantitative. The curves could be modeled, predicted, and compared across populations. They were not stories told by individual galaxies. They were statements made by gravity itself. As astronomers refined these measurements, they noticed something else. The shapes of rotation curves correlated with the amount of visible matter present, suggesting a deep relationship between ordinary matter and dark matter distributions. This did not undermine the dark matter idea. Instead, it hinted at how galaxies form. Ordinary matter falls into gravitational wells created by dark matter. As stars ignite and evolve, their feedback reshapes gas, subtly influencing the distribution of both components. The connection was dynamic, not mysterious. This insight moved dark matter from a static explanation to an active participant in cosmic evolution. It was not merely adding weight, it was guiding formation. The rotation curves were snapshots of this history, frozen in motion. Each curve encoded the past interactions between visible matter and an unseen gravitational scaffold. The confidence gained from rotation curves set the stage for broader questions. If dark matter surrounded galaxies, did it also dominate larger structures? If it shaped individual systems, did it also sculpt the universe as a whole? The problem was no longer whether dark matter existed in some isolated contexts. The question became how deeply it was woven into cosmic architecture. As attention shifted outward, from individual galaxies to collections of them, the same theme emerged with increasing strength. Motion continued to exceed visible mass. Structures remained bound when they should not have been. Gravity kept revealing more influence than light could explain. And with each new scale examined, the idea that dark matter was an incidental fix became less tenable. Rotation curves had done their work. They transformed suspicion into necessity. They forced astronomers to accept that something massive, invisible, and pervasive was present around every galaxy they could measure. Whatever dark matter was, it was not rare. It was not optional. It was the dominant gravitational component shaping galactic motion. And, as this realization settled in, it became natural to ask whether galaxies themselves were only part of a much larger pattern, whether the same unseen mass governed the behavior of entire clusters of galaxies, binding them together across millions of light years, and revealing its presence not through light, but through the relentless, patient logic of gravity acting on everything that moves. Clusters of galaxies provided the next unavoidable step, because they removed any lingering doubt that dark matter might be a peculiarity of individual systems. A galaxy cluster is one of the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies moving within a shared gravitational field. The distances are immense, the timescales long, and the motions slow enough to be measured with confidence. If unseen matter truly dominated galaxies, its influence should become even more apparent when many galaxies interact together. When astronomers measured the velocities of galaxies inside clusters, they found speeds that were far too high to be explained by visible matter alone. Galaxies were moving as if they were embedded in a deep gravitational well, far deeper than the combined mass of stars and gas could create. If that extra mass were not present, clusters would have dispersed long ago, their galaxies drifting apart over cosmic time. Instead, clusters remain coherent, long-lived structures, quietly stable over billions of years. This was not simply a matter of motion. Clusters are filled with hot gas, heated to tens of millions of degrees and glowing brightly in X-rays. This gas contains far more mass than all the stars in the cluster combined. Yet, even when this gas is included in the mass budget, the gravitational pull still falls dramatically short of what is required. The gas itself should escape unless something far more massive holds it in place. Again, gravity pointed to something unseen. The presence of this hot gas also ruled out a tempting alternative explanation. if the missing mass were simply faint stars, cold planets, or clouds of dust. Their gravitational influence would be accompanied by heating, collisions, and radiation. The gas would behave differently. Its temperature, distribution, and motion would betray the presence of such ordinary matter. Instead, the gas responded to gravity as if the dominant mass passed through it almost without interaction. One particularly striking example comes from systems where clusters collide. In these events, galaxies pass through one another relatively unharmed, while the hot gas clouds interact, slow down, and heat up through friction. By mapping the distribution of mass using gravitational lensing, astronomers can see where gravity is strongest during and after the collision. What they find is profound. The bulk of the gravitational mass follows the galaxies, not the gas. The dominant mass component behaves as though it barely notices the collision, continuing on its path while ordinary matter lags behind. This separation between visible matter and gravitational influence is extraordinarily difficult to explain without invoking dark matter. Modified gravity alone cannot easily account for why gravity would appear strongest where little ordinary matter remains. The simplest explanation is that most of the mass in the cluster consists of particles that interact weakly, pass through collisions unimpeded, and reveal themselves only through gravity. Clusters, therefore, act as natural laboratories. They amplify the effects seen in individual galaxies and strip away ambiguity. On these scales, uncertainties in stellar populations, gas distributions, or internal dynamics become secondary. The gravitational signal is overwhelming. Something massive and invisible dominates the system. What emerges from clusters is not just confirmation, but refinement. Dark matter must be largely collisionless. It must not clump or dissipate energy the way ordinary matter does. It must form large, extended halos that overlap and merge as structures grow. These are not speculative traits. They are properties demanded by observation. At this point, dark matter ceased to be an isolated solution to a local problem. It became a central ingredient in the story of structure itself. Galaxies form within clusters. Clusters trace filaments. Filaments connect across vast distances. Everywhere gravity sculpts the universe on large scales, the same unseen mass appears to be doing most of the work. As observations extended outward and backward in time, attention naturally turned to another consequence of mass that does not shine. If dark matter truly fills space and bends gravity everywhere, it should also bend light itself, subtly reshaping the images of distant objects and revealing its presence even where motion alone cannot be measured. Light itself became the next messenger, because gravity does not only guide motion, it shapes space, and anything moving through space, including light, must follow that shape. When light from a distant galaxy passes near a massive object, its path curves. The image stretches, distorts, or splits, not because the light has changed, but because the geometry it travels through has been altered. This effect, gravitational lensing, was predicted long before it could be observed, and when it finally was, it offered a new way to see mass without relying on motion at all. Astronomers began to notice faint but systematic distortions in the shapes of distant galaxies. Individually, these distortions were subtle, barely perceptible. But when many galaxies were analyzed together, patterns emerged. Their shapes were aligned in ways that could not be explained by chance or by the galaxies themselves. Something in the foreground was bending, their light. By carefully mapping these distortions, scientists could reconstruct the distribution of mass responsible for them, creating gravitational maps of regions of space. What these maps revealed was striking. The mass traced by lensing did not align neatly with visible matter. In many cases, the strongest lensing signals appeared in regions with few stars and little gas. Conversely, bright concentrations of ordinary matter sometimes produced less lensing than expected. Once again, gravity was responding to something unseen, something spatially extended and dominant. Lensing was especially powerful because it did not depend on the internal state of galaxies or clusters. Stars could be young or old, gas hot or cold, systems calm or disturbed. Light bending cared only about mass. This made lensing a clean probe, free from many of the uncertainties that complicate other measurements. When lensing and motion told the same story, confidence deepened. In colliding galaxy clusters, lensing offered perhaps the clearest visual separation between ordinary matter and dark matter. As clusters passed through one another, their hot gas clouds collided and slowed, glowing brightly in X-rays. The galaxies themselves, mostly empty space, passed through with little interaction. Lensing maps showed that the bulk of the mass followed the galaxies, not the gas. The gravitational centers were offset from the brightest matter. This spatial divorce between mass and light was difficult to ignore. At this point, dark matter was no longer defined only by what was missing. It had a shape. It had a distribution. It formed halos around galaxies and clusters, overlapping and merging as structures grew. It was smooth on small scales compared to ordinary matter, and dominant on large ones. These properties emerged not from theory alone, but from the convergence of multiple observational techniques. With lensing, astronomers could now see dark matter even where motion was chaotic or difficult to interpret. They could map it in regions where galaxies were forming, merging, or tearing apart. The unseen became traceable, not directly, but reliably. Gravity was acting as a translator, converting invisible mass into visible effects. This growing picture raised a deeper question. If dark matter shaped galaxies and clusters, it must have been present from very early times. Its influence should be imprinted not just in structures we see today, but in the earliest light the universe released. The universe itself, in its infancy, should carry a record of how much dark matter existed and how it behaved. That record exists as a faint glow permeating all of space, the afterglow of the Big Bang, released when the universe cooled enough for light to travel freely. Tiny variations in that glow encode information about matter, energy, and gravity in the young cosmos. By studying these variations with exquisite precision, scientists can infer the total amount of matter, how it clustered, and how it interacted. What those measurements revealed was consistent with everything learned from galaxies and clusters. Ordinary matter made up only a small fraction of the total. Dark matter dominated the mass budget, shaping the growth of structure from the very beginning. Without it, the universe would look profoundly different. Galaxies would form later, less efficiently and with less order. The familiar cosmic web would never have emerged. By this stage, dark matter was no longer a hypothesis waiting for confirmation. It was a framework supported by independent lines of evidence across vast scales and epochs. The remaining mystery was no longer whether dark matter existed, but what it was made of, how it behaved at the particle level, and why it interacted so weakly with everything else. The silence of dark matter in detectors on Earth, Its refusal to reveal itself through light or collisions became part of its identity rather than a flaw. It told physicists where not to look, narrowing possibilities and guiding theory. Each non-detection carved away at the space of ideas, shaping a clearer outline of what dark matter could be. As understanding deepened, the focus shifted again, from seeing dark matter's effects to asking how it fits into the fundamental laws of physics. Whether it arises from undiscovered particles, subtle extensions of known forces, or something even more delicate, its gravitational voice continues to speak clearly. And as the evidence accumulates, the universe maintains its calm consistency. Stars move, light bends, structures grow. In all of it, the same unseen influence persists, not dramatic, not hidden in shadows, but present everywhere gravity quietly keeps time, inviting a closer look at what kind of substance can shape everything while remaining almost entirely unseen. As the picture expanded backward toward the early universe, one consequence became unavoidable. If dark matter dominates gravity today, it must have dominated it when the universe was young, dense, and hot. At that time, everything was closer together, and small differences mattered enormously. Tiny variations in density were amplified by gravity, growing over time into the first structures. Understanding what grew first tells us what was present first. In the earliest moments after the Big Bang, ordinary matter was tightly coupled to radiation. Photons scattered constantly off charged particles, preventing matter from collapsing under gravity. Dark matter, by contrast, did not interact with light. It felt gravity, but not radiation pressure. This difference allowed dark matter to begin clumping earlier, forming subtle gravitational wells, while ordinary matter was still smoothed out by light. These early wells became the seeds of all later structure. As the universe expanded and cooled, light gradually decoupled from matter, freeing ordinary particles to fall into these pre-existing wells. Gas flowed inward. Density increased. Stars ignited. Galaxies took shape where dark matter had already gathered. This sequence is not speculative storytelling. It is encoded in the statistical patterns of the cosmic microwave background, the faint relic radiation that fills the universe. That background is remarkably uniform, yet it contains tiny fluctuations in temperature, 1 part in 100,000. Those fluctuations correspond to variations in density in the early universe. By measuring their size, spacing, and distribution, scientists can infer the relative amounts of different components of the cosmos. The data show a universe composed mostly of dark matter and dark energy, with ordinary matter making up only a small fraction. Crucially, the pattern of these fluctuations depends on how matter behaves. If all matter interacted strongly with radiation, the pattern would look very different. Peaks would be shifted, smoothed, or suppressed. The observed pattern matches a universe in which most matter does not interact with light, but still contributes gravitationally. Dark matter is not an add-on here. It is written into the earliest observable light. Simulations reinforce this picture. When cosmologists model the universe using only ordinary matter, the result is a diffuse, understructured cosmos. Galaxies form too late, too sparsely, and with the wrong distribution. When dark matter is included, structure emerges naturally. Filaments stretch across space. Voids open up. Galaxies cluster along invisible scaffolding. The simulated universe begins to resemble the one we observe. This success does not mean dark matter is fully understood. It means its gravitational role is well constrained. Whatever dark matter is, it must be cold or at least slow-moving early on, so it can clump efficiently. It must be stable over cosmic time. It must interact weakly enough to avoid disrupting the delicate pattern seen in the background radiation. These requirements narrow the field sharply. At this stage, the question of dark matter shifts subtly. It is no longer about explaining anomalies. It becomes about identifying a physical substance that fits a precise profile. Particle physicists enter the story here, not to invent freely, but to test candidates against strict cosmic rules. Some possibilities arise naturally in extensions of known physics. Others are constrained or ruled out by observation. Experiments on Earth attempt to detect dark matter directly, watching for tiny recoils when a dark matter particle brushes past an atomic nucleus. Others search indirectly, looking for signals that might arise if dark matter particles annihilate or decay. So far, these searches have been quiet. No unambiguous signal has appeared. But this quiet is informative. It tells us dark matter interacts extremely weakly, if at all, with ordinary matter beyond gravity. That weakness is not a disappointment. It is consistent with everything learned so far. Dark matter's defining feature is restraint. It shapes the universe without glowing, colliding, or clumping the way ordinary matter does. It is present everywhere, yet almost nowhere detectable directly. Its influence is slow, cumulative, and patient. As observations sharpen and theories evolve, the outline of dark matter becomes clearer even as its substance remains hidden. It is not a catch-all for ignorance. It is a specific solution demanded by multiple independent facts. Each fact alone might be questioned. Together, they form a coherent, stable picture. What remains remarkable is how this unseen component brings order rather than confusion. It explains why galaxies rotate the way they do, why clusters remain bound, why light bends where little matter is seen, and why structure formed when it did. Dark matter does not complicate the universe. It simplifies it, allowing gravity to operate consistently across scales. And still, the question remains open at its deepest level. Not whether dark matter exists, but what kind of entity can fulfill all these roles while remaining almost entirely invisible. The universe continues to answer indirectly, through motion, through light, through structure, offering constraints instead of revelations, guiding inquiry with quiet consistency as the search moves ever closer to the fundamental nature of this unseen mass that shapes everything we see and much that we do not. As this understanding settled, attention naturally narrowed toward the smallest scales, because if dark matter shaped the universe so profoundly, it must arise from something fundamental. Gravity alone describes how it behaves, but not what it is. To move forward, physicists turned to the language of particles, not to speculate freely, but to ask which kinds of particles could exist without contradicting everything already observed. Any viable candidate had to satisfy a demanding list of conditions. It had to be massive enough to account for the gravitational pull we see, yet interact so weakly that it remained invisible to telescopes. It had to be stable over billions of years, otherwise it would have decayed away. It had to move slowly enough in the early universe to allow structures to form, yet not clump or collide like ordinary matter. These requirements were not negotiable. They were imposed by galaxies, clusters, and the earliest light itself. One class of candidates emerged naturally from extensions of known physics. These hypothetical particles would interact through gravity and possibly the weak nuclear force, but not through electromagnetism. In the early universe, they would have been produced abundantly, cooling as space expanded, settling into the halos inferred from observation. Their properties fit comfortably within the constraints, not because they were invented to do so, but because the mathematics allowed them to exist without breaking established laws. Another possibility involved particles so light and numerous that they behave less like individual grains and more like a continuous field. In this picture, dark matter would have wave-like properties on astrophysical scales, subtly smoothing structure in ways that might resolve small discrepancies between simulations and observations. These ideas are explored carefully, tested against data, and adjusted or discarded as evidence demands. The process is slow, deliberate, and grounded. What matters here is not which candidate ultimately proves correct, but how tightly the universe has guided the search. Dark matter is not free to be anything. Its gravitational effects constrain its mass, its speed, its interactions, and its abundance. Every experiment that fails to detect it directly sharpens those constraints, carving away possibilities and refining the shape of the answer. This sharpening has a calming quality. The silence of detectors does not mean failure. It means consistency. Dark matter behaves exactly as something that interacts almost exclusively through gravity should behave. It slips through ordinary matter without notice. It leaves no tracks except in the motion of stars and the bending of light. It reveals itself statistically, collectively, patiently. In this sense, dark matter invites a different relationship with knowledge. It asks us to trust indirect evidence, to accept that reality does not always announce itself through sensation. Some of the most influential components of the universe do their work quietly, shaping outcomes without ever becoming the focus of attention. Dark matter does not glow, but without it, galaxies would not exist as they do. It does not collide, but without it, structure would unravel. As research continues, the question, what is dark matter, remains open but not empty. It is filled with constraints, measurements, and understanding. Each observation adds weight to a picture that is already coherent, even if incomplete. The universe has told us how dark matter behaves. It has shown us where it is and how much of it there must be. What it has not yet done is reveal its substance. That final step may come through a subtle signal in a detector, a deviation in a spectrum, or a new consistency uncovered in cosmic structure. Or it may require a deeper shift in how fundamental physics describes matter itself. Whatever the path, it will not overturn what has already been learned. It will fit into it, because the gravitational story is already written across the sky. Dark matter, then, is not a shadow hiding behind the universe. It is a framework holding it together, revealed not by brightness, but by balance. It is present in every rotation curve, every lensing map, every filament stretching between clusters. It shapes the cosmos without demanding attention, leaving us with a question that grows quieter and more precise as understanding deepens, waiting not for a dramatic revelation, but for the moment when the invisible finally becomes gently known. The more precisely dark matter was constrained, the more it reshaped how physicists thought about absence itself. In everyday experience, what cannot be seen is often treated as empty, as nothing. In cosmology, that intuition fails. Dark matter is not a gap in understanding where anything might hide. It is a presence defined by its effects with unusual clarity. Its invisibility is not vagueness, it is specificity. This distinction matters because it separates dark matter from earlier scientific placeholders that eventually vanished. The ether dissolved when better experiments showed light did not need it. Dark matter, by contrast, persists because removing it breaks too many things at once. Take it away, and galaxies lose their stability. Take it away, and the early universe cannot grow structure fast enough. Take it away, and gravitational lensing loses its coherence. Dark matter is not propping up a single theory. It is stitching many together. What has become increasingly clear is that dark matter behaves less like a substance that participates in the busy chemistry of the universe and more like a quiet background condition. It sets the stage on which visible matter acts. Stars burn, explode, and fade. Gas cools and heats. Galaxies collide and merge. Through all of this, dark matter remains largely unchanged, responding only to gravity, reshaping itself slowly as structures grow and combine. This stability gives dark matter a kind of memory. Its distribution today carries information about conditions long past. By mapping dark matter halos and comparing them with simulations, scientists can infer how fast particles moved in the early universe, how clumpy matter was shortly after the Big Bang, and how gravity competed with expansion over cosmic time. Dark matter becomes a record keeper, not through marks or traces, but through structure. On the smallest scales, subtle tensions appear. Some dwarf galaxies seem to have less dense dark matter cores than simulations predict. Others show patterns that hint at interactions between dark matter and ordinary matter during formation. These discrepancies are not failures of the framework. They are refinements, places where additional physics or complex feedback may be at work. Importantly, they occur at the edges, not at the foundation. This is how mature scientific questions behave. The center becomes solid, while the boundaries invite exploration. Dark matter's central role is no longer in doubt. What remains is texture. How smooth is it really? Does it ever interact weakly with itself? Could there be multiple types? These questions do not reopen the case for existence. They deepen the inquiry into nature. Throughout this process, gravity remains the unifying thread. It is gravity that revealed the problem. Gravity that constrained the solution. Gravity that continues to act as the translator between the visible and the unseen. Dark matter reminds us that gravity is not merely a force between objects, but a storyteller, encoding information in motion, shape, and structure. In this light, dark matter becomes less mysterious and more intimate. It is not hiding. It is everywhere, doing exactly what it must do to produce the universe we observe. Its silence is not secrecy, but restraint. It does not announce itself because it does not need to. Its work is already done, written into the sky on scales so vast that only patience can reveal them. As experiments continue and observations sharpen, the question, what is dark matter, remains open, but it no longer floats freely. It rests on a firm landscape of evidence, shaped by decades of careful attention. Whatever the final answer turns out to be, it will not rewrite this story. It will settle into it, explaining why the universe has been moving the way it has all along, why gravity has been so consistent in its demands, and why something unseen has always been present, quietly shaping everything that comes into view, even now, as understanding advances slowly enough to match the calm persistence of the cosmos itself. What quietly emerges from all of this is a shift in how certainty feels. Dark matter is not uncertain because evidence is weak. It is uncertain because the evidence is strong but indirect. The universe has told us repeatedly and consistently how dark matter behaves, where it is concentrated, and how much of it exists. What it has withheld is the simplest kind of familiarity. There is no glow to point at, no substance to hold, no interaction to feel. Knowledge here comes not from contact, but from coherence. This coherence is why dark matter has endured scrutiny rather than eroding under it. Every new observation has tightened its outline instead of dissolving it. When telescopes mapped galaxies earlier in cosmic history, dark matter was already there. When simulations included it, structure formed naturally. When they excluded it, the universe fell apart too slowly or not at all. These outcomes are not interpretive. They are mechanical. They follow from gravity, doing what gravity always does. In this sense, dark matter teaches an unusual lesson about realism. Something can be profoundly real without ever becoming directly accessible. Reality does not require visibility. It requires consequence. Dark matter's consequences are everywhere. They appear in how galaxies rotate, how clusters bind, how light bends, how patterns in the early universe froze into place. Remove dark matter, and these consequences unravel together. This interlocking quality matters. Scientific explanations are strongest when they explain many things at once without strain. Dark matter does this quietly. It does not require separate fixes for separate problems. One assumption, that most matter does not interact with light, resolves discrepancies across scales spanning billions of light years and billions of years. That economy is not aesthetic. It is diagnostic. The search for dark matter particles continues not because the cosmic case is weak, but because it is strong, enough to justify the effort. Experiments grow more sensitive. Detectors listen more patiently. Theoretical models refine their predictions. This is not a race toward revelation. It is an alignment process, bringing fundamental physics into harmony with what the universe has already revealed gravitationally. There is also a humility embedded in this process. Dark matter reminds us that the universe is under no obligation to be composed only of things that resemble us or our instruments. Ordinary matter interacts richly, producing light, chemistry, and life. Dark matter does not. It occupies a different role, one that supports complexity without participating in it. The universe appears to require both. As this realization settles, the original question changes character without changing form. What is dark matter is no longer a demand for immediate identification. It becomes an invitation to recognize how much can be known without full disclosure. We already know its abundance. We know its distribution. We know its gravitational behavior across time. The remaining unknown is not vast. It is precise. This precision is why progress feels slow but steady. Each new constraint rules something out. Each non-detection narrows the field. The absence of surprise is itself informative. Dark matter continues to behave exactly as something almost entirely governed by gravity should behave. It neither reveals hidden complexity nor contradicts expectation. It simply persists. In the long view, this persistence is reassuring. It suggests that the universe is intelligible even when parts of it remain unseen. Patterns can be trusted. Inference can be reliable. Understanding does not require spectacle. Sometimes it arrives through patience, through consistency, through effects that never go away no matter how carefully we check. Dark matter remains one of those effects. It does not flicker. It does not fade. It does not depend on any one measurement or method. It is there in motion, in structure, in light, bent ever so slightly from its path. It is there because gravity says it must be. And so the inquiry continues, not urgently, not dramatically, but with a quiet confidence that whatever dark matter turns out to be, it will not overturn what has been learned. It will complete it. It will explain why the universe has always behaved as though something unseen was present, steady and reliable, shaping everything gently from behind the scenes, long before we learned how to notice. As this quiet confidence takes hold, it becomes easier to see why dark matter has resisted simple resolution. The universe has not presented it as a dramatic anomaly demanding urgent repair. Instead, it has integrated dark matter so thoroughly into its behavior that removing it would unravel the whole fabric of explanation. Dark matter is not a loose thread. It is part of the weave. This perspective reshapes how progress is measured. Discovery here does not look like a sudden reveal, but like increasing alignment. Models grow more constrained. Simulations grow more faithful. Observations grow more precise. Each step reduces freedom rather than adding speculation. Dark matter's nature is being cornered gently, not chased. What also becomes clear is that dark matter occupies a middle ground between the cosmic and the fundamental. It is not merely a large-scale effect, nor merely a particle-scale curiosity. It sits between, linking the physics of the very small with the architecture of the very large. Whatever it is must be consistent with both realms at once. That dual demand is rare, and it is what makes dark matter such a powerful guide. This guiding role extends even to what dark matter is not allowed to do. It cannot disrupt the smoothness of the early universe beyond what is observed. It cannot erase small galaxies entirely. It cannot cluster too tightly or spread too diffusely. It cannot interact too strongly or too weakly. Each of these limits comes from data, not preference. Dark matter is constrained from every side. In that sense, the universe has already done most of the work. The remaining task is interpretive rather than exploratory. The shape of the answer exists before the substance fills it in. Physicists are not searching blindly. They are matching candidates to a template written in gravity and time. This process carries an unexpected calm. There is no urgency to force a conclusion. Dark matter has waited billions of years. It will wait longer. Understanding proceeds at the pace required for coherence, not speed. Each generation of instruments listens a little more carefully. Each generation of theory speaks a little more precisely. And throughout this patience, the original question remains intact, neither weakened nor inflated. What is dark matter is still the right question, asked in the right way. It does not demand mystery. It demands clarity. It does not ask for wonder. It earns it. Dark matter reminds us that the universe is not obligated to reveal itself through the senses we evolved with. Some of its most important components operate outside the narrow channels of light and touch. Yet they are not inaccessible. They are legible through pattern, through motion, through consistency. They can be known without being seen. As attention continues to narrow, the space of possibilities shrinks, and the unknown becomes sharper rather than larger. Dark matter's identity is not drifting away. It is coming into focus slowly, like a shape emerging not from brightness, but from shadow cast consistently across everything that moves. And so the universe continues to speak in the same quiet language it always has. Stars orbit, light bends, structures persist, gravity keeps time. Within all of this, dark matter remains present, not as a riddle placed there to frustrate understanding, but as a reminder that some truths reveal themselves only through patience, through accumulation, through listening carefully to what never stops happening, even when nothing new seems to appear. As this narrowing continues, an interesting inversion takes place. Early on, dark matter was introduced to explain what could not be explained otherwise. Now, it has become the reference against which everything else is tested. New observations are not asking whether dark matter fits, but whether they are consistent with the dark matter framework already established. In most cases, they are. Large sky surveys map millions of galaxies at once, tracing how matter clusters across enormous volumes of space. The statistical patterns that emerge align with a universe dominated by dark matter that moves slowly, clumps efficiently, and interacts weakly. These patterns are not decorative. They encode the growth of structure over billions of years. When dark matter is included, the statistics make sense. When it is removed, coherence dissolves. Even the expansion history of the universe carries its imprint. Dark matter contributes to how fast structures grow compared to how fast space stretches. By measuring how galaxies cluster at different epochs, astronomers can infer how gravity competed with expansion across time. The results consistently point to the same balance of components. Dark matter plays its role steadily, neither overwhelming nor negligible. What is striking is how little freedom remains. The universe has left very little room for improvisation. Dark matter cannot be hot and fast-moving, or it would smear out small structures. It cannot be strongly interacting, or it would collapse and glow. It cannot be rare, or galaxies would not form as they do. Each property is fixed not by theory, but by observation. The picture is constrained almost to the point of inevitability. This inevitability carries a quiet emotional weight. It suggests that the universe is not hiding its workings out of indifference, but revealing them in the only language available at scale. Light tells part of the story. Motion tells another. Structure tells a third. Together, they converge on a single conclusion with remarkable patience. As research continues, some physicists explore whether dark matter might have subtle interactions beyond gravity, interactions so weak they have escaped detection so far. Others consider whether multiple components might exist, each contributing differently at different scales. These ideas are explored carefully, not to destabilize the framework, but to refine it where observations invite nuance. What remains unchanged is the central role dark matter plays in making the universe legible. Without it, gravity would not knit matter into the patterns we see. Without it, the universe would be flatter, emptier, slower to organize. Dark matter is not an embellishment. It is the reason complexity had time to arise. At this stage, the question, what is dark matter, no longer feels impatient. It feels settled enough to wait. The universe is not rushing to answer, and neither is science. Understanding accumulates not through dramatic turns, but through alignment, through the slow matching of theory to a reality that has been consistent all along. Dark matter continues to do what it has always done. It anchors galaxies. It binds clusters. It shapes the cosmic web. It bends light gently, almost apologetically, just enough to reveal its presence to those who look carefully. It remains unseen, not because it is hidden, but because it does not belong to the luminous side of existence. And, as attention stays with this quiet presence, it becomes clear that dark matter is less a missing piece than a different kind of piece altogether. Not something added to complete a picture, but something already there, waiting for the picture to grow large enough to include it, guiding motion, structure, and time itself with a steadiness that has never wavered, even as our understanding continues to move closer, step by careful step. As this picture settles even further, a subtle shift occurs in how dark matter is understood emotionally as well as scientifically. It stops feeling like an unknown waiting to be uncovered and begins to feel like a background condition of reality, something closer to space-time itself than to any familiar substance. Not because it is abstract, but because its influence is so uniform and persistent that it frames everything else rather than standing out from it. In this framing, dark matter is not an actor stepping onto the cosmic stage. It is the stage's underlying structure. Galaxies do not merely contain dark matter, they are shaped within it. Their visible components trace paths already laid down by something that does not participate in light or chemistry, but quietly determines where gravity is strongest and where it thins out. Ordinary matter follows. It responds. It decorates what dark matter makes possible. This helps explain why dark matter feels so difficult to isolate. We are accustomed to studying things by interacting with them directly, by shining light on them, colliding them, heating them, or breaking them apart. Dark matter offers none of these handles. It does not resist, scatter, or glow. It allows itself to be known only through consequence. This is not a limitation of technology alone. It is a feature of the thing itself. Yet even this restraint carries information. The fact that dark matter does not interact strongly means it preserves the early universe remarkably well. While ordinary matter is churned by stars, explosions, radiation, and turbulence, dark matter changes slowly. Its distribution today still echoes conditions from billions of years ago. In this way, it acts as a cosmic fossil, holding on to memory long after visible matter has forgotten. When astronomers compare dark matter maps to the locations of galaxies, they see this memory at work. Galaxies form where dark matter density peaks, but their subsequent evolution can blur that relationship. Star formation, feedback, and mergers rearrange luminous matter. Dark matter remains smoother, quieter, more faithful to the original gravitational blueprint. It is less reactive, less expressive, but more reliable. This reliability is why dark matter anchors modern cosmology. It provides a stable reference frame against which change can be measured. Without it, the universe would be harder to read. Patterns would be more chaotic, histories more ambiguous. Dark matter simplifies interpretation by staying consistent while everything else evolves. At the same time, this consistency does not make dark matter boring. It makes it profound. Something that shapes nearly everything while remaining almost entirely unchanged itself occupies a rare position in physics. It suggests that the universe requires components that do not compete for attention, that do not transform rapidly, that do not participate in complexity, but enable it. Seen this way, dark matter is less like a missing puzzle piece and more like the silence between notes in music. It does not draw focus, but without it, structure collapses into noise. The analogy ends there, but the intuition lingers. Presence does not always announce itself through activity. Sometimes it is defined by steadiness. As research continues, this steadiness becomes a guiding constraint. New theories must respect it. New observations must align with it. dark matter has earned a kind of authority, not through direct detection, but through consistency across domains that rarely agree so cleanly. Galactic dynamics, gravitational lensing, cosmic background radiation, and large-scale structure all converge on the same quiet conclusion. This convergence is why dark matter has survived so many challenges. Each challenge has forced refinement rather than retreat. Each apparent discrepancy has either dissolved with better data or opened a narrow, controlled space for deeper physics. The core has remained intact. What remains unresolved now feels less like ignorance and more like patience. The universe has already told us most of what it intends to say through gravity. The final layer, the particle identity or deeper mechanism, will not overturn that message. It will complete it gently, fitting into a framework that has been stable for decades. Until then, dark matter continues to do what it has always done. It shapes motion without motion of its own. It governs structure without participating in it. It binds without touching. It influences without signaling. And through all of this, it remains present everywhere gravity operates on large scales, offering a kind of quiet reassurance that the universe, even in its unseen majority, is orderly, consistent, and ultimately knowable, even if knowing arrives slowly enough to match the calm with which everything has always moved. As this understanding matures, the role of dark matter begins to feel less provisional and more structural. It is no longer waiting on discovery to justify its place. It has already justified itself through coherence. The remaining unknown is not whether it belongs in our description of the universe, but how deeply it is woven into the laws that govern everything else. This perspective brings a subtle calm to the question. There is no pressure for dark matter to suddenly reveal itself in a dramatic way. Science is no longer asking it to prove its existence. That work is done. What remains is a quieter kind of curiosity, the kind that listens rather than demands. The universe has already spoken clearly through gravity. Now it is being asked to whisper through particles, fields, or symmetries that we have not yet fully learned to hear. In many ways, dark matter has already changed physics, even without being directly detected. It has reshaped how galaxies are modeled, how simulations are built, how surveys are designed, and how cosmology is taught. It has become part of the background knowledge against which new ideas are tested. Any proposed modification to gravity, any new particle theory, any revision of cosmic history must now pass through the narrow gate that dark matter has defined. This gatekeeping role is not arbitrary. It arises from the fact that dark matter links otherwise separate realms of knowledge. It connects the motion of stars to the statistics of primordial radiation. It ties the formation of galaxies to the behavior of particles in the early universe. Few concepts in physics span such a wide range of scales with such consistency. That alone gives it weight. There is also something revealing about how dark matter resists anthropocentric intuition. Ordinary matter feels familiar because it interacts richly. It emits light, forms structures we can touch, supports chemistry and life. Dark matter does none of this. It is indifferent to complexity. It does not participate in feedback loops or self-organization in the way luminous matter does. And yet, without it, complexity would not arise at all. It provides the gravitational patience that allows time for stars to form, planets to settle, and life to emerge. Seen this way, dark matter occupies a supporting role that is easy to overlook precisely because it does its job so well. It does not draw attention to itself. It does not vary dramatically from place to place. It does not announce transitions or events. It remains steady across billions of years, shaping outcomes without becoming one. That steadiness is its defining feature. As observational techniques continue to improve, this steadiness becomes an advantage. Subtle deviations, if they exist, will stand out against an otherwise smooth background. Precision surveys, deeper lensing maps, and more sensitive detectors are not searching randomly. They are probing carefully chosen edges where dark matter's behavior might reveal a hint of its deeper nature. Even if such hints take a long time to appear, the framework remains intact. Dark matter has already earned its place not by being fully understood, but by being unavoidable. It is required not by one observation, but by many, all pointing in the same direction. This convergence is rare in science, and it carries a quiet authority. What this leaves us with is not an unsolved mystery in the dramatic sense, but an open chapter written with unusually clear margins. The universe has told us how much dark matter there is, where it resides, how it behaves gravitationally, and how it influenced the formation of everything we see. The remaining question of what it is made of is narrow, technical, and deep. It belongs not to cosmology alone, but to the foundations of physics. And so the question, what is dark matter, continues to do its work, not as a challenge, but as a guide. It keeps inquiry focused. It keeps speculation grounded. It keeps attention aligned with evidence rather than imagination. In doing so, it exemplifies a particular kind of scientific beauty, one that emerges not from spectacle, but from patience, from consistency, and from the quiet confidence that the universe, even in its unseen majority, behaves in ways that can be understood, given enough care, enough listening, and enough time. As this patience continues, something else becomes visible, not in data, but in how the question itself behaves. Questions that are poorly formed tend to fragment. They spawn competing explanations that never quite meet. Questions that are well formed do the opposite. They pull diverse observations inward, aligning them without force. What is dark matter has proven to be one of those questions. It has aligned astronomy and particle physics, observation and theory, the early universe and the present one. It has done so without requiring frequent revision of its core premise. This stability is unusual. Many scientific ideas pass through cycles of enthusiasm and correction. Dark matter has instead passed through cycles of refinement, becoming narrower, more precise, and more constrained with time. That refinement has changed the emotional texture of the search. Early on, dark matter felt like a problem to be solved. Now it feels more like a condition to be understood. There is a difference. Problems invite fixes. Conditions invite accommodation. Dark matter has shaped the universe for billions of years. It will not be rushed into clarity on human timescales. This realization subtly shifts attention away from urgency and toward resolution. The goal is no longer to force dark matter into an existing category, but to allow the correct category to emerge. That may involve new particles, new symmetries, or deeper principles that connect gravity to the quantum world. Whatever form it takes, it will have to respect the calm consistency already written into cosmic structure. In the meantime, dark matter continues to function as the universe's quiet majority. Most of the mass is not luminous. Most of the gravitational influence does not announce itself. Most of the scaffolding of reality, operates without interacting with light or chemistry. This is not a flaw in our understanding. It is a statement about how the universe chooses to organize itself. There is something grounding in this. It reminds us that importance is not measured by visibility. The most influential components of the cosmos do not need to be dramatic or accessible. They need only to be reliable. Dark matter has been reliable across every scale at which it has been tested. As observations extend deeper into space and further back in time, this reliability becomes more pronounced. Young galaxies already show the influence of dark matter. Ancient light already encodes its presence. The universe did not transition into a dark matter-dominated state recently. It began that way. From the very start, gravity's balance depended on something unseen. This continuity makes dark matter feel less like an addition to cosmology and more like one of its foundations. Space expands, time flows, gravity acts. Dark matter participates in that triad quietly, consistently, without demanding interpretation. It simply is, doing what it has always done. And yet, even as this calm settles in, curiosity remains active. The question does not fade. It sharpens. What kind of entity can exist everywhere, influence everything gravitationally, and remain almost entirely absent from all other interactions? That is not a vague question. It is a precise one, and precision is where progress eventually happens. The search continues not in expectation of surprise, but in trust that coherence will deepen. Dark matter has already shown that the universe is willing to be understood on its own terms, even when those terms differ from our instincts. It asks us to listen longer, to infer more carefully, to accept that some truths reveal themselves not through direct encounter, but through the steady accumulation of consequence. And so, the motion of stars continues to trace invisible paths. Light continues to bend around unseen mass. Structures continue to grow along filaments no telescope can see directly. In all of this, dark matter remains present, not as an enigma demanding attention, but as a constant influence shaping everything quietly, faithfully, and without interruption, even as understanding continues to move closer, one careful step at a time. As attention settles into this steady rhythm, the scale of what dark matter enables becomes harder to ignore. It is not simply holding existing structures together. It determined which structures could exist at all. In the early universe, matter was almost perfectly smooth, with only tiny ripples in density. Those ripples mattered because gravity amplifies difference. Where density was slightly higher, gravity pulled more strongly, drawing in surrounding matter and deepening the contrast. Without dark matter, this amplification would have been slow and inefficient. Expansion would have outpaced collapse. The universe would have remained diffuse for much longer. Dark matter changed that balance. Because it did not interact with radiation, it began clumping early when ordinary matter was still locked in a glowing plasma. These early clumps were not dramatic. They were subtle concentrations, barely distinguishable from their surroundings. But they were persistent. As the universe expanded and cooled, these concentrations remained, providing gravitational anchors that ordinary matter could finally respond to. Gas flowed inward. Compression increased. Cooling followed. Stars ignited. The visible universe assembled itself around an invisible framework that had been in place all along. This sequence is important because it reveals dark matter as a prerequisite rather than a consequence. Galaxies did not form and then acquire dark matter. dark matter gathered first, and galaxies formed because of it. This reverses an intuitive assumption and replaces it with a deeper one. Visibility is not a measure of primacy. The most influential components may operate long before they can be noticed. As simulations of cosmic evolution improved, this idea became clearer. When dark matter is included, the simulated universe develops a filamentary structure that closely matches what surveys observe. Matter arranges itself into threads and knots, separated by vast voids. Galaxies trace these threads, clustering where dark matter density is highest. When dark matter is removed from the simulation, this architecture collapses. Structures form too late, too weakly, or not at all. The universe loses its characteristic texture. This texture is not cosmetic. It affects how galaxies evolve, how gas flows between them, how clusters grow, and how environments differ across cosmic regions. Dark matter does not dictate the details of these processes, but it sets the conditions under which they unfold. It defines where gravity dominates and where it thins out. Everything else responds. This responsiveness highlights another subtle property. Dark matter does not erase diversity. Galaxies still differ in shape, size, and history. Clusters still vary in richness and dynamics. Dark matter provides a common scaffold, not a uniform outcome. It enables complexity without enforcing sameness. This balance between structure and freedom is one of its most remarkable features. As observational reach extended, astronomers began to see this scaffolding at earlier and earlier times. Galaxies, observed when the universe was only a few billion years old, already show signs of being embedded in dark matter halos. Even the earliest known galaxies appear where dark matter simulations predict they should. This agreement across time reinforces the idea that dark matter has been present and influential from the very beginning. At the same time, dark matter's behavior remains strikingly simple. It responds to gravity and little else. It does not fragment into smaller bound objects the way ordinary matter does. It does not radiate energy and collapse further. It remains extended, diffuse, and smooth on small scales relative to stars and gas. This simplicity is not assumed. It is inferred from the absence of effects we would otherwise see. If dark matter interacted strongly with itself, halos would behave differently. They would develop dense cores or show signs of internal heating and cooling. If it interacted strongly with ordinary matter, it would leave traces in stars, planets, or detectors. The fact that none of this is observed tells us that dark matter occupies a narrow behavioral niche. It is massive but aloof, influential but reserved. This aloofness has consequences for how galaxies change over time. Ordinary matter cycles through phases. Gas becomes stars. Stars explode and enrich gas with heavier elements. Feedback from stars and black holes reshapes galactic environments. Dark matter does not participate in these cycles. Its distribution changes only through gravity, slowly adjusting as galaxies merge or accrete mass. This difference in timescale creates a separation between visible history and invisible structure. In some cases, this separation becomes visible indirectly. When galaxies collide, their stars may pass through one another with little interaction, while gas clouds collide violently and shock. Dark matter, inferred through lensing and dynamics, passes through as well, barely noticing the encounter. The visible aftermath can be chaotic, but the underlying dark matter halos continue on relatively undisturbed. This resilience reinforces the idea that dark matter is not easily perturbed. Because of this, dark matter halos retain information about mergers long after visible signs have faded. Streams of stars can trace past interactions, but the overall halo structure encodes an even longer memory. By studying these halos, astronomers can reconstruct aspects of galactic history that are otherwise lost. Dark matter becomes a kind of archive, preserving gravitational events across cosmic time. This archival role extends beyond individual galaxies. On the largest scales, the distribution of dark matter reflects the initial conditions of the universe itself. Tiny quantum fluctuations stretched by cosmic expansion became the seeds of all structure. Dark matter amplified those seeds faithfully, without adding complexity of its own. As a result, the large-scale structure of the universe today still reflects those primordial patterns. In mapping dark matter, we are indirectly mapping the universe's earliest moments. This connection between the smallest and largest scales is one of dark matter's most profound implications. It links quantum fluctuations to galaxy clusters, early time to late time, simplicity to complexity. Few components of nature bridge such extremes so seamlessly. Dark matter does not merely fill space, it connects eras. Despite this, the question of its fundamental nature remains unresolved. Is dark matter a particle, a field, or something even more subtle? Current evidence favors particulate explanations because they integrate naturally with known physics and reproduce observations well. Yet, even within that category, possibilities vary widely in mass, interaction strength, and origin. Each candidate must navigate the same narrow corridor defined by cosmic evidence. Experiments designed to detect dark matter directly continue to refine their sensitivity. Underground detectors isolate themselves from noise, waiting for rare interactions. Space-based instruments search for indirect signals. Particle accelerators probe energies where new physics might appear. None of these efforts operate in isolation. They are guided by astrophysical constraints, ensuring that searches remain focused rather than speculative. The absence of detection so far has not weakened the case. Instead, it has strengthened certain conclusions. Dark matter must interact extremely weakly with ordinary matter. It must be stable. It must be abundant. Each non-detection sharpens these statements. This process is slow, but it is cumulative. Knowledge grows through exclusion as much as through discovery. This mode of progress can feel unsatisfying if one expects dramatic breakthroughs, but it is deeply consistent with the nature of the phenomenon. Dark matter has always revealed itself indirectly. It would be surprising if its final identification arrived in a loud or abrupt way. More likely, it will emerge as the last remaining option that fits everything we already know. In the meantime, dark matter continues to serve as a reminder of how science often advances. Not through singular moments of revelation, but through the steady alignment of many independent threads. Each thread alone might fray. Together, they form a fabric strong enough to support confidence. That confidence does not mean closure, it means orientation. We know where we are looking. We know what properties matter. We know what cannot be true. This clarity allows curiosity to remain calm rather than anxious. The question persists, but it does so within well-defined boundaries. Dark matter also invites a broader reflection on the limits of perception. Much of what shapes reality lies beyond immediate experience. Forces act without being seen. Structures exist without emitting light. Causes precede effects by vast spans of time. Understanding requires patience, inference, and trust in consistency. Dark matter exemplifies all of this. As attention stays with this idea, it becomes easier to accept that the universe is not built primarily for observation. Light is one channel among many. Gravity is another. Dark matter speaks through the latter. It communicates not through brightness, but through balance. Not through events, but through persistence. This persistence has been uninterrupted. From the earliest moments after the Big Bang to the present cosmic web, dark matter has behaved the same way. It has not changed phase, decayed, or transformed. It has simply continued to shape the universe by being there. That continuity is rare and valuable. It provides a fixed reference in a cosmos otherwise defined by change. In that sense, dark matter offers a kind of stability that extends beyond physics. It shows that influence does not require visibility, that importance does not require interaction, and that understanding does not require immediacy. Some truths reveal themselves only through long attention to what remains constant while everything else evolves. The question, what is dark matter, remains open, but it no longer feels restless. It feels settled enough to support deeper inquiry. It has become a question that holds space rather than demands answers, guiding investigation gently while respecting the universe's pace. And, as gravity continues to trace invisible paths through motion and light, dark matter remains present, steady, and quietly essential, shaping the universe with a patience that mirrors the care with which we are slowly learning to understand it. As this patience deepens, it becomes possible to notice something subtle about how dark matter changes our sense of scale. In everyday life, influence is usually local. Touch affects what is nearby. Light illuminates what it reaches. Sound fades with distance. Dark matter does none of this in a familiar way. Its influence accumulates across vast spans of space, acting gently but persistently, shaping outcomes not through intensity but through duration. It is not strong in the moment. It is strong over time. This long timescale influence is why dark matter is so closely tied to gravity rather than to any other force. Gravity itself is weak in comparison to electromagnetism or the nuclear forces, yet it dominates the universe on large scales because it adds rather than cancels. Dark matter amplifies this additive quality. By contributing mass without introducing complexity, it allows gravity to remain simple while becoming decisive. The universe grows structure not through sudden force, but through steady imbalance. Seen this way, dark matter is not merely an ingredient. It is a condition that allows gravity to matter at all on cosmic scales. Without it, gravity would still exist, but its reach would be limited. With it, gravity becomes the architect of galaxies, clusters, and filaments. Dark matter does not replace gravity. It gives gravity something to work with. This relationship also explains why dark matter appears smooth where ordinary matter is clumpy. Ordinary matter sheds energy. It cools, collapses, fragments, and forms dense objects. Dark matter does none of this. It retains a diffuse character, spreading its mass over large volumes. This diffuseness is not accidental. It follows directly from the absence of strong interactions. Dark matter cannot radiate away energy, so it cannot collapse into compact objects the way stars do. It remains extended, quietly shaping the potential wells in which everything else evolves. Because of this, dark matter halos are often much larger than the visible galaxies they host. A galaxy may appear as a bright island of stars, but it sits deep within an invisible ocean of mass that extends far beyond its luminous edge. The visible portion is only the central glow of a much larger structure. This inversion of expectation is one of dark matter's most important lessons. What we see is not what dominates. This dominance also reshapes how motion is interpreted. When stars orbit within a galaxy, they are not orbiting the visible matter alone. They are responding to the combined gravitational field of stars, gas, and dark matter together. This field changes smoothly with distance, reflecting the extended nature of the dark matter halo. The resulting motion feels natural once the halo is included. Without it, motion feels inexplicable. Dark matter restores simplicity. The same is true for clusters of galaxies. Their internal motions, gas temperatures, and lensing patterns all align when dark matter is included. The system behaves like a gravitational whole. Without dark matter, it becomes fragmented and unstable. Once again, dark matter acts as the element that allows disparate observations to converge. This convergence is perhaps the most important feature of all. Dark matter is not supported by one line of evidence, but by many that reinforce one another. Each method measures something different. Motion measures response to force. Lensing measures curvature of space. Background radiation measures early conditions. Large-scale surveys measure statistical distribution. That all of these point to the same unseen component is not trivial. It is rare. Because of this, dark matter occupies a special place in scientific confidence. It is not provisional in the way speculative ideas are. It is conditional only in its identity, not in its necessity. Something like dark matter must exist, even if its ultimate description differs from current candidates. The universe demands it. This demand has consequences for how future discoveries will be interpreted. If a new particle is detected that matches the required properties, it will not rewrite cosmology. It will settle into it naturally. If no such particle appears, physics will be forced to rethink deeper assumptions about gravity or space-time itself. But even then, the gravitational phenomena will remain. Motion will still need explanation. Structure will still need scaffolding. The universe will still insist on coherence. This insistence is what makes the question enduring rather than frustrating. Dark matter does not represent a failure of understanding. It represents understanding at a boundary. We have reached the edge of what can be inferred from gravity alone. Beyond that edge lies microphysics, fields, symmetries, or mechanisms not yet fully accessible. The boundary itself is well defined. That is an achievement. It is also worth noticing how dark matter reframes humanity's place in the cosmos. Everything familiar, everything that emits light, everything that forms atoms and chemistry and life, makes up only a small fraction of the total mass. Most of the universe is made of something that does not participate in these processes at all. This is not diminishing. It is clarifying. It shows that the conditions for complexity arise within a much larger, quieter context. Life exists not because matter is abundant in its familiar form, but because the gravitational environment created by dark matter allowed time and structure to emerge. Stars formed in stable galaxies. Heavy elements were produced and dispersed. Planets assembled in long-lived orbits. All of this required gravitational stability over billions of years. Dark matter provided that stability indirectly, by shaping the environment in which ordinary matter could behave richly. This indirect support is easy to overlook because it does not announce itself. Dark matter does not interact with chemistry or biology. It does not care about planets or life, and yet without it, none of these would exist as they do. Influence does not require intention, it requires consistency. As understanding continues to mature, dark matter begins to feel less like an anomaly and more like an invitation. It invites physics to extend itself gently, respecting what is already known while opening space for what is not. It invites cosmology to remain grounded in observation while reaching toward deeper explanation. It invites patience. That patience is already paying dividends. The space of possible explanations is shrinking. Constraints from astrophysics, cosmology, and particle physics are converging. The outline is becoming sharper. The remaining unknown is not sprawling. It is narrow and deep. It may take time to fill, but the shape is clear. Until then, dark matter continues to be present everywhere gravity operates on large scales. It continues to guide motion without friction. It continues to bend light without emitting it. It continues to structure the universe without participating in its visible drama. It remains steady, reliable, and indifferent to attention. And perhaps that is its final lesson. Not everything that matters announces itself. Some of the most important components of reality operate quietly, shaping outcomes without spectacle. They ask to be understood through patience rather than immediacy, through coherence rather than sensation. Dark matter has shaped the universe in this way from the beginning. It has never rushed. It has never changed its behavior. It has simply been there, allowing gravity to do its work over vast spans of time. As understanding continues to move closer, it does so at a pace that mirrors the phenomenon itself, slow, steady, and guided not by urgency, but by the quiet confidence that what is real, even when unseen, leaves traces that can always be followed, given enough care, enough listening, and enough time. As this quiet continuity stretches on, another layer of understanding begins to settle into place, one that has less to do with discovery and more to do with trust. Trust in gravity as a reliable narrator. Trust in patterns that repeat across scale and time. Trust that when many independent measurements point in the same direction, they are revealing something real, even if it cannot yet be touched. Dark matter has earned that trust through repetition. Every time astronomers measure motion, they find the same excess. Every time they map mass through lensing, they find the same unseen structures. Every time they reconstruct the early universe from relic light, they find the same proportions. This repetition is not monotonous, it is stabilizing. It tells us that the universe is not improvising its behavior from one era to the next. It is following rules that are consistent even when they involve components we do not yet fully understand. This consistency is why dark matter has become central, rather than peripheral. It is no longer something added to explanations as needed. It is something explanations are built around. Models of galaxy formation begin with dark matter halos. Simulations of cosmic evolution assume dark matter from the first moment they begin. Observational strategies are designed with dark matter's influence already in mind. It has become part of the default landscape. Once this shift occurs, the question, "What is dark matter?" changes subtly again. It becomes less about resolving a discrepancy and more about characterizing a dominant constituent. The universe is telling us that most of its mass does not behave like the matter we are made of. understanding that difference is no longer optional. It is essential to understanding the universe as it actually is, rather than as we might have expected it to be. This realization has philosophical weight, but it arises directly from physics. The universe does not privilege what is familiar. It does not organize itself primarily around light, chemistry, or life. Those emerge later, within a much larger context defined by gravity and mass. Dark matter occupies that context. It is the background against which complexity becomes possible, not because it encourages complexity, but because it provides stability. Stability is a recurring theme here. Dark matter stabilizes galaxies by deepening their gravitational wells. It stabilizes clusters by binding their members. It stabilizes cosmic structure by allowing density variations to grow rather than wash out. Even the expansion history of the universe reflects this stabilizing role, balancing the pull of gravity against the stretching of space. Without dark matter, this balance would tip differently, and the universe would not look the way it does. Yet, dark matter achieves this stability without rigidity. Structures still evolve, galaxies still merge, clusters still grow. Dark matter halos respond to these changes, reshaping themselves through gravity alone. This responsiveness without dissipation is unusual. Ordinary matter responds through collisions, heating, cooling, and radiation. Dark matter responds through motion and redistribution, nothing more. It is flexible without being reactive. Because of this, dark matter halos can overlap and interpenetrate during mergers, gradually settling into new configurations. They do not shatter or fragment. They do not lose energy abruptly. They adapt slowly. This slow adaptation preserves large-scale coherence even through violent events. Galaxies can collide spectacularly while their dark matter halos pass through one another almost transparently, maintaining the deeper gravitational structure. This transparency is not mysterious. It follows directly from weak interaction. Dark matter particles, whatever they are, do not scatter off one another or off ordinary matter in any significant way. They move through space as if it were almost empty, responding only to the cumulative pull of mass. This makes their behavior simple to model and difficult to disturb. The simplicity of dark matter behavior has practical consequences. It allows cosmologists to simulate the universe with remarkable fidelity, using relatively few assumptions. Given an initial distribution of dark matter and the laws of gravity, large-scale structure emerges naturally. Ordinary matter can then be layered on, adding complexity without altering the underlying framework. This layered approach works because dark matter provides a stable foundation. It is worth pausing on how unusual this is. In many areas of physics, adding complexity introduces fragility. Systems become sensitive to small changes. Predictions become unstable. With dark matter, the opposite happens. Adding it simplifies explanations and strengthens predictions. This inversion is one of the strongest arguments for its reality. As the field has matured, attention has turned toward subtle questions about dark matter's internal properties. Does it interact with itself at all? Is it perfectly cold? Or does it have a small velocity dispersion? Does it come in one species or many? These questions are not asked lightly. Each one has observable consequences. Self-interaction would alter halo shapes. Warm motion would suppress small-scale structure. Multiple components would leave distinct imprints. Observations constrain all of these possibilities tightly. So far, the simplest picture continues to hold. dark matter appears cold, collisionless, and dominant. This does not mean the simplest picture is guaranteed to be correct. It means that if complexity exists, it must hide within narrow bounds. Nature is allowed nuance, but not contradiction. This narrowing is where progress lives now, not in sweeping revisions, but in careful tests at the margins. Dwarf galaxies are studied because their small size makes them sensitive to dark matter properties. Gravitational lensing is mapped with increasing precision to reveal fine structure in halos. Cosmic surveys extend to earlier times to test how structure growth depends on dark matter behavior. Each of these efforts is guided by the same underlying framework. The calmness of this process mirrors the phenomenon itself. Dark matter does not demand attention. It allows itself to be studied slowly, indirectly, patiently. It does not produce dramatic signals or sudden surprises. It reveals itself through consistency rather than eventfulness. Science adapts to this by slowing down, refining tools, and trusting accumulation over spectacle. This adaptation is not resignation, it is alignment. When the subject of study is subtle, the method must be subtle too. Dark matter has taught cosmology how to listen carefully, how to infer responsibly, and how to accept that some aspects of reality are legible only through long integration of evidence. In this way, dark matter has shaped not just our picture of the universe, but our approach to understanding it. It has reinforced the value of coherence across scales, the importance of independent confirmation, and the power of negative results. Each of these lessons extends beyond dark matter itself. As the universe continues to expand and structures continue to evolve, dark matter remains unchanged in its role. It does not age. It does not transform. It does not decay. It continues to provide the gravitational backdrop against which everything else unfolds. This timelessness is part of its identity. It is not tied to specific epochs or events. It is present throughout cosmic history. This presence invites a kind of quiet respect. Not awe in the dramatic sense, but appreciation for steadiness. In a universe defined by change, something that remains consistent across billions of years stands out, even if it does not shine. The question, what is dark matter, remains open, but it is no longer lonely. It is supported by a network of understanding that grows denser with time. Each new observation strengthens that network rather than pulling it apart. The unknown sits within the known, framed and constrained. And as this framing becomes more complete, the remaining gap feels less like ignorance and more like anticipation. Not anticipation of a sudden reveal, but of a gentle alignment, where one more piece settles into place and the picture becomes clearer without changing its character. Until that moment arrives, dark matter continues to shape everything quietly, reliably, and without interruption. It bends light just enough to be noticed. It guides motion just enough to matter. It structures the universe without participating in its visible drama. And through all of this, it reminds us that reality does not owe us immediacy, only consistency, and that understanding often comes not from seeing more, but from learning how to listen to what has been there all along. As this long continuity settles in, the role of dark matter begins to feel almost architectural. Not in the sense of design or intention, but in the way certain elements make other possibilities viable simply by existing. An arch holds because of its shape, not because it announces itself. Dark matter holds the universe together in a similar way, through presence rather than action, through mass rather than interaction. This architectural role becomes clearer when considering how fragile cosmic structure actually is. On large scales, the universe is expanding. Space itself stretches, carrying galaxies away from one another. Gravity must constantly work against this expansion to maintain coherence. Ordinary matter alone is not enough to win that contest early on. Dark matter tips the balance just enough to allow gravity to sculpt structure before expansion thins everything out. It does not stop expansion. It competes with it, quietly and persistently. This competition leaves a measurable imprint. The rate at which structures grow over time reflects the relative strengths of gravity and expansion. By observing how galaxy clustering changes across cosmic history, scientists can infer how much dark matter must be present and how it behaves. Once again, the answer is consistent. Dark matter grows structure steadily, neither too aggressively nor too weakly. The universe evolves in a way that is balanced, not extreme. Balance appears again and again in this story. Dark matter is not dominant in every sense. It does not overwhelm ordinary matter locally. It does not erase the effects of radiation, gas dynamics, or feedback. Instead, it sets boundary conditions. It defines the gravitational landscape within which other processes operate. This is a subtle kind of dominance, one that enables rather than dictates. Because of this, dark matter also influences what kinds of galaxies can exist. The mass of a dark matter halo affects how much gas it can retain, how quickly that gas cools, and how efficiently stars form. Small halos may lose gas easily, forming faint dwarf galaxies. Larger halos can sustain star formation over longer periods, producing massive spirals or ellipticals. Dark matter does not determine the details of these outcomes, but it constrains the possibilities. These constraints are visible in galaxy populations across the universe. Certain types of galaxies are common, others are rare. Some environments favor rapid star formation, others suppress it. Behind these trends lies the distribution of dark matter halos, setting the stage on which visible matter evolves. The diversity of galaxies emerges not despite dark matter, but because of the range of environments it creates. This range is another important point. Dark matter is not uniform. It clusters, forming halos of different masses. These halos merge hierarchically, small ones combining to form larger ones over time. This process, known as hierarchical structure formation, is a direct consequence of dark matter's properties. Because it is cold and collisionless, it builds structure from the bottom up. Small structures form first, larger ones assemble later. Observations support this picture. The oldest galaxies tend to be small. Massive clusters appear later. The growth history inferred from observations matches the predictions of dark matter-driven models. This agreement extends across many datasets, reinforcing the idea that dark matter's behavior has been correctly identified at a fundamental level, even if its composition remains unknown. Composition, however, continues to matter. Knowing what dark matter is made of would connect cosmology to particle physics in a profound way. It would reveal whether dark matter arises naturally from extensions of known theories or whether it points to entirely new principles. It would tell us whether the universe contains more hidden structure at the smallest scales, not just the largest. Yet, even here, the universe sets boundaries. Dark matter can't interact too strongly, or it would have altered early cosmic patterns. Cannot decay appreciably, or it would leave detectable signatures. It cannot be too light or too fast, or small-scale structure would be erased. These constraints carve out a narrow space in which dark matter must reside. The challenge is not finding any explanation, but finding the right one. This narrowing of possibilities is sometimes misunderstood as stagnation. In reality, it is progress of a particular kind. Science advances not only by discovering new things, but by ruling out wrong ones. Each excluded possibility clarifies the landscape. Dark matter research has excluded vast regions of theoretical space, focusing attention on what remains viable. This is a quiet but powerful form of understanding. It also reflects a maturity in the field. Early excitement often tolerates broad speculation. As evidence accumulates, speculation becomes disciplined. Dark matter research has reached this disciplined phase. Ideas are proposed carefully, tested rigorously, and discarded without drama if they fail. The framework remains intact because it is anchored in observation, not preference. Throughout this process, the universe continues to behave as it always has. Stars orbit, galaxies merge, clusters evolve, light bends. None of these phenomena pause while we refine our theories. They proceed according to gravity's rules, indifferent to our understanding. Dark matter's role in these processes is constant. It does not respond to being studied. It simply continues to exist. This indifference is instructive. It reminds us that knowledge is not something the universe provides on demand. It is something we extract patiently by noticing patterns that persist regardless of interpretation. Dark matter has been one of the most persistent patterns of all. It has remained present across decades of observation, across generations of instruments, across shifts in theoretical fashion. Because of this, dark matter has reshaped what counts as evidence. Direct detection, once seen as the gold standard, is now understood as only one piece of a larger puzzle. Indirect evidence, when consistent and convergent, can be equally compelling. Dark matter teaches that reality does not always announce itself through direct interaction. Sometimes it reveals itself only through influence. This lesson extends beyond cosmology. It applies to any domain where causes are separated from effects by scale, time, or accessibility. Understanding often requires trusting inference when inference is supported by coherence. Dark matter exemplifies this trust, not as belief without evidence, but as confidence built from many independent confirmations. As the universe continues to expand, the influence of dark matter will gradually diminish relative to that expansion. Structures will stop growing. Clusters will become isolated. Galaxies beyond our local group will drift beyond reach. Yet even in this distant future, dark matter will remain present within bound structures, continuing to shape them quietly. Its role may change in relative importance, but it will not disappear. This long view adds another layer of calm. Dark matter is not a fleeting phenomenon tied to a particular cosmic era. It is a durable component of reality, present in the past, active in the present, and likely relevant far into the future. Its influence spans cosmic history. Understanding such a component requires patience equal to its timescale. It requires methods that integrate over vast distances and long durations. It requires theories that respect both the smallest and largest scales. It requires humility about what can be known directly and what must be inferred. All of these requirements have shaped modern cosmology. In that sense, dark matter has already done important work beyond its gravitational role. It has trained the field to be careful, integrative, and patient. It has encouraged collaboration between disciplines. It has emphasized consistency over novelty. As inquiry continues, the question, what is dark matter, remains central, not because it is unresolved, but because it connects so much of what we know. It sits at the intersection of gravity, structure, and fundamental physics. Answering it fully would not just fill in a blank. It would deepen our understanding of how the universe organizes itself at every level. Until then, dark matter continues to exist exactly as it has for billions of years, shaping outcomes without announcement. It remains unseen not because it is hidden, but because it belongs to a different category of existence, one defined by influence rather than interaction. And as long as gravity continues to guide motion and bend light, dark matter will continue to leave its quiet signature everywhere the universe reveals itself, waiting patiently as understanding moves, slowly and steadily, closer. As all of this settles, the question no longer presses forward with urgency. It rests. Dark matter does not ask to be chased or forced into clarity. It asks to be noticed for what it has always done, shaping motion, holding structure, guiding the universe quietly from its earliest moments to now. Nothing about it is rushed. Nothing about it is theatrical. Its influence has always unfolded on timescales far longer than attention, far broader than sight. What remains is a sense of steadiness. The universe behaves as though dark matter is there because it is. Galaxies continue to move the way they must. Light continues to bend the way it always has. Structure continues to persist where gravity allows it. The unseen does not feel absent anymore. It feels integrated, woven so thoroughly into the fabric of things that it no longer stands apart as a mystery, but sits comfortably as part of the landscape that makes everything else possible. Understanding does not close around it. It relaxes around it. The question remains open, but it is no longer restless. It has found its place, supported by evidence, shaped by patience, and grounded in a universe that has been quietly consistent all along. If this quiet journey brought you a moment of calm, a gentle like or a soft tap on subscribe truly helps keep this calm corner of the universe glowing. And tell me, where in the world are you listening from tonight? Rest well until our next quiet journey.